All right. Hi, good afternoon, everyone. How are you today? Good? I see a lot of happy faces. Hopefully you are happy from inside. All right. So today we'll continue with the 5th lecture. This is Advanced Computer Architecture course. And hopefully this is the last lecture on caches. We spend a lot of time, but this is really important to set the stage for memory design. Next lecture, we're going to start with the DRAM device. So this lecture will be more on the practical side. We will have some exam questions on the slides. And I'm going to ask you to solve it over here. That's why I have a pile of papers and pencil, so you don't have any excuse. This will be part of the 20% of attendance and participation. You don't have to worry. We'll take a lot of examples during the class, and then I will ask you to apply it over one of the questions. Should be easy. Should be just part of the attendance. The second thing that is really important, we announced the schedule of talks. So hopefully you don't have any conflict. This is really important to move forward. Do we have any conflict? Okay, that's great. Yeah, we try to take all consideration. We receive a lot of emails, those who's traveling or attending some weddings. Who's attending wedding? Not here, okay. Yeah, so we try to accommodate everyone. So we already fixed the schedule based on that. But if you still have any worries about the time, the date, the topic, the paper, just let us know. Or you can send to supper and we can discuss it. All right, so we started last time over replacement policy. This is really important. How, if the cache is really full, or if the set in the cache is already full, how we can replace one of those blocks and add the new one, okay? And we went through several of these algorithms. We discussed random very briefly last time. FIFO, first in, first out. This is a trivial way of doing that. Least recently used. What does it mean? Least recently used. It means we already used it in the past, right? So it's already exists in the cache. That's why we are replacing it. And we didn't use it recently within a time frame, okay? We have also not most recently used, and we said this is not this, right? But this is somewhere in between, but could include also the least recently used, because it's not most recently used, right? By definition, it's the opposite to this, but this also bigger circle or bigger set than those least recently used, because it could be not least, not most, somewhere in between. We have also least frequently used, right? So based on the frequency, how many times we request or we send a request to access that block, right? Least costly to refetch. So now we try to talk about cost, and the cost thing is something subjective, right? There is no single cost here, right? The cost could be time, which is latency, right? Do we need to access it from very far place and bring it to the cache or to the CPU? But could be also a miss rate, right? So this is one of the important metrics on improving the performance. If we miss that block many times, of course, we are going through very long trip to bring that block to the CPU. There is also hybrid replacement policies, which is currently used in modern CPU. We are not using single policy to replace the block. Why? Because we don't expect user to run workload that is homogeneous, for example, that's show the exact same pattern over time. So user normally run a lot of application. Each of them show really different pattern over the CPU, over these accesses from the CPU to the memory. For example, we got an example of AI intensive application. Those who send a lot of memory requests and do a little over the CPU, very small number of computation, right? Same with the games. Most of the time we are rendering new scenes in the game, right, on the screen. And those require accessing a lot of data in the memory to fetch those blocks and display them over to the user. But also, we see some benefits coming from adding more to the hierarchy of the caches. So for example, L4 cache, right? Sometimes we see some benefits, sometimes we don't see that benefits. Today we will focus on the LRU, which is least recently used, plus 2 more policies to replace those blocks. The first one called minimizes miscount, or that is the goal of the policy. The policy itself called Belady OPT, which is optimal algorithm, or they claim to be optimal. And we discussed last time, what does optimal mean in this context? We don't have single optimal, right? Optimal could be really depending on the metric that we are targeting. And we said the optimality of Belady algorithm is basically reducing the miss rate, okay? So they are optimal in reducing the miss rate. The other algorithm we'll go through, we'll take several questions on that, called MLP-Aware or awareness, that aim to reduce the isolated miss. MLP stands for? No, this is different. Memory-Level Parallelism. Memory-Level Parallelism. Why? Because it does consider the hierarchy, the entire hierarchy of fetching block over that hierarchy. And what does isolated miss mean? Raise your voice, please. Separated. What does it mean? Shared space, yeah, you are close there, but the first part, no, it's not correct. Isolated miss, that means we have 2 types of misses, right? One of them is isolated, the other one is? Raise your voice. Shared miss by the core. Excellent, but we call it something else. That is the meaning of it, but what we call it? Yes, someone? Excellent. You deserve chocolate? Yeah, it's correct. Maybe both of you. Yeah, that's correct. So we have isolated miss and parallel miss. What is the difference between these two? What is the difference between isolated miss and parallel miss? Probably the name could explain itself. So parallel miss is that we send a request in parallel to 2 blocks, right? Or we send 2 different requests to the same block. So at the same time, we could supply or answer these requests in the same time. It means we don't have to wait double the time to get these 2 blocks. So the memory controller and the CPU send 2 requests to the memory. Please give me those 2 blocks, or we send 2 requests to get the same block. How that could happen if we send 2 requests to obtain the same block? Remember, last time we drew that the CPU normally has many cores, right? And each of these cores normally has its own L1 cache, right? And then we have L2 cache that could be private, which means 1 L2 cache per core, right? So we could have L1 and L2 per core. And then the L3 normally shared between the cores. So normally the L3 is shared between all these cores. So imagine that both cores send 2 requests, each of them 1 request, to get the same block. So in this way, the memory controller are going to manage that, right? Getting through the memory and get those 2 blocks or same block, and then supply it to the CPU. In this way, we wait only once. So we have this block, the second block. This is not necessarily to be perfectly aligned with the first block, right? Or the first request. It could be like slightly after, slightly before, right? However, some time or some latency is overlapped between these 2 requests. And normally we call those computationally cheap, okay? Because we pay only once to bring 2 blocks or to answer 2 misses. In the isolated domain or isolated mess, we send 1 request. There are no parallel requests to that block or to that request. And there is another request, and so on. So the number of requests over here, or number of blocks that we are asking for, is going to determine or to scale proportionally to the latency. So if one mess is costing us 50 nanosecond, right, then the 3 requests are going to cost us 150. Okay, that's why they are expensive. All right, now let's go through these examples or questions. Hopefully you will understand and you will challenge yourself to solve them. First question. So this is a real exam question. Okay, this is normally how we ask this question. We don't ask you direct questions to give us how the cache act or how they replace those blocks. So it says, consider a processor with the following configuration. So the first thing, it's in order execution. What does it mean? In order means it executes the instructions one by one in sequential order, right? It does not allow for jumping between the instruction to do some parallel execution. So if you read the code that's provided, you could really follow line by line. You don't have really to jump. There is no way of jumping between the lines. The second given instruction is that we have a single L1 data cache, single L1. So we don't have L2, we don't have L3. It's just single cache. Let's see some properties of that cache. First, it's fully associative. Hopefully by now you already understand this clearly. What does it mean?
Index and tag.
Indexing?
Index and tag are unique for each data.
No, directly mapped is something else, right? So we have direct mapped, we have n-way associative cache, then we have the next level, fully associative. What does it mean?
We can keep.
We can. The entire cache is one set. Excellent. Yeah, next time, this time you'll get it by hand. Thanks. Yeah, the fully associative means the entire cache is a single set. It means I'm free to place the block anywhere. I'm not restricted to any region in the cache. Okay, this is really important. In direct map, I'm only allowed to place a block in single location. Okay, this is a huge difference between both. Fully associative mean I'm free to place that block anywhere in the cache. Direct map, just I have single location to place that block based on the LSB of the address. The capacity of that L1 cache is 2 cache blocks. What does it mean? Means I can always fit up to 2 blocks. If I have 3 blocks to fit them in the cache, no, sorry. You can only place 2 at the time. And if you want to fit the third one, you have to replace something from the cache out, bring in the third one. Okay? A programmable replacement policy. So you have 2 options that you can program the replacement policy yourself. You can now activate this or activate that. Okay? What are the 2 options? LRU, least recently used, and Belady algorithm, which is the optimal one. We will see now what does it mean. The system configuration has 2 memory access paths. Okay, so we have the CPU, we have the memory controller over there, and memory controller is responsible for issuing those commands to bring me more data from the DRAM, right? And the data could come through this path or the other path. What is the difference? The first path has L1 cache in it, right? So we check always the L1 cache. Do you have that block? If no, it means a miss. Then we move to the next level in the hierarchy. Next level here, we don't have L2 cache, we don't have L3. So next level directly is the DRAM, right? So we're still in the same path. Now the other path we don't have any caches. Okay, so this is very trivial design, no caches, directly to the DRAM. However, there's always penalty between those paths. The first one, if we get a hit, what will happen? What is the penalty? 10 cycles, excellent. If we get a hit, means the data exists in the L1 cache, then we pay only 10 cycles to bring that block to the CPU. Now, if we get a miss, 30. Excellent, 30. So 10 plus 20, it's not only 20. So if we get a miss, means the data is not here, so we have to go to the DRAM, bring it to the cache, and then from the cache to the CPU. So the cost, the total cost is 30 cycles. Okay. Now the second path, there is no cache, means there is no miss, there is no hit. There is always hit, always the data in the DRAM. Of course, we can add an SSD over there and make it a bit more complex, right? And then if we don't have the data in the DRAM, we have to go to the SSD, bring the data to the DRAM, back to the CPU. But in this example, we don't have storage. So the final destination, the DRAM, it's always hit and it costs us 25 cycles. OK. Now we're still in the question. Now all of those are given to you. Now the question is, you are a computer architect at OpenAI. What is OpenAI? ChatGPT, right? All of you know it. You are required to optimize the execution time of the following performance critical program. And this is really how those companies designing their own processor. Okay? They have a piece of code, for example, Tesla processor. We saw it last time. How we decide on what is the optimal cache size, for example. They were using what cache size in Tesla chip? 32 megabyte, right? So always should be to the power of 2. Don't forget it. All right, so we are given this code. Supposed to be, this is Tesla self-driving car code. And you are required to optimize it to make it faster in terms of architecture. We don't care about software level now. We care about the architecture, the underlying hardware that's running your code. You are giving this hint. The load block N represents loading a cache block from the DRAM to the cache at location N. So we have here several of those instructions: loading a block 1, loading block 2, loading block 3. Now, if you look carefully to the code, what you will see? You'll see first a for loop, right? We are initializing a variable I with values 0, right? And then we have a condition over here, right? Every time we iterate over the entire thing, we do some increment over here. What is this increment? I equal I plus 1. So we add 1 to the I. And then we do the modulus sign over 5. What does it mean?
Resets that I to
One of you.
4. Remainder
Of?
when I plus 1.
Excellent. So whenever it's multiple of 5, right, then the remaining is 0, right? And before that, if it is not 5, it is 4. 4. It is 3, 3. If it is 2, 2, and so on. If it is 6, 1, right? So anything between the multiple of 5s is the same value or deducted with 5. Okay? So that means we iterate from I equals 0, and then we execute the entire thing over here, and then we increment it by 1, then modulus 5, it's 1. So we start with I equals 0, then I equal 1, I equal 2, I equals 3, I equals 4, and then? Now with 4 plus 1, modulus 5 is 0. So this will take us back to this, right? And keep iterating over that. Now, with the first one, we can see sometimes we execute this, sometimes we execute that, sometimes we execute this, sometimes we execute 3 of them. Why? because I less than 3, okay, let's assume it's 0, then this is greater than 0, so this will not be executed when it's 0. This will be greater than 1, then it will not be executed when it's 0, right? So we can see there is alternation between these 3 commands. Now, if you look carefully about it, I want to save your time, so this is what you'll see. In the first iteration, we load only block 1. Next iteration, block 1 and 2, then 1 and 2 and 3, then 2 and 3, then 3, and iterate. Okay? This is really what this code is doing. If you're not convinced, just look closely at it. Try to give an examples or values to I, and you'll see this pattern. Okay? Now, hopefully you understand the question. You have solid state, stand on top of, and then let's solve the question. So again, all of these are the given one. I summarized them for you. Okay, this is the path, the 2 paths that we have. Now there is one missing from the previous explanation, that you are allowed to choose one of these paths at once. Okay, every time you are allowed to choose one of these paths. You cannot access both paths to bring a block. Okay, so you choose either this or that, and that choice is not up to you. It's up to the question. The question will ask you that you are allowed to not use the second path at all, for example. Then you only use that path. The question sometimes asks you that you are allowed to use this path only to fetch block 2, for example. Okay, so block 1 and 3 should go through this path, but this should only be for block 2. It can also ask you that this path can be used for block 2 and 3, for example. Okay, and then block 1 will be through the path number 1, and the other blocks will go through the second path. Is it clear? All right. Now we are going to, this is kind of way to assist you to organize your answer. We're going to have a table, right? These are the number of iteration. Remember, those are assigned with every time we access a block. So I0 will access only block 1. I1, we have 2 cases because first we need to access block 1 and then block 2. Okay? And then I equal 2, we are going to access 3 blocks. So we have 3 rows, 2 rows, single row, then iterate. The question asks you now to use only least. Please close laptops, close all laptops. Unless you're really in stock market, as we discussed last time, then you are allowed to use laptops. Okay. Least recently used, and we are considering 1 iteration of the loop. Not only that, this is again miss rate. Do you still remember the definition of miss rate? We've discussed this too many times. What is it? Number of misses over total of? Yes? Total of? What do we send from memory controller to the DRAM? What do we send? Memory accesses, memory request. How many times we request blocks? How many of them don't exist in the caches, right? That is the miss rate. So number of misses over the total number of requests. And it makes sense, the definition. We have also another definition, which is number of misses per instruction. Okay, then we have to divide over instruction to take the average number of misses that is caused by single instruction. But currently, we just are interested in miss rate, okay? Not miss rate per instruction. Now, in the first case, you're not allowed to use the second path at all, okay? Uncached load instruction is none. So none of the blocks allow you to use the second path, okay? Do you have papers, plain paper? I have here some pen, some empty paper. Please feel free to take any. Please write down your name, student ID, that will be considered as participation and attendance. Please try to answer the question. The question is really easy. We're going to go through it step by step. Again, I have plain papers over here. I have pens, so feel free to take some. Please close all laptops. course, SEPA can still use laptop. Oh, yeah. Yeah, finally, I can see some movement in the class, which is something nice I like. I can see some energy. So you need just to fill this table. So the table has, in the first column, the number of iteration. So the first one, we are going to request in I0, what we are going to request? Block 1. We are going to request block 1 from the DRAM or from whatever, but we are not allowed to use the second path. So we are only allowed to use this path. Now, initially, you can assume the cache is totally empty. Totally empty. What is the status of the cache in I0? Here, you can draw the number of blocks that exist in the cache. Okay, over here in the second column, the number of blocks, for example, 1, 2, 3, 5, 4, whatever. The number of blocks that already exist in the cache before you start. Okay, are you done? Sorry. Here you need to write the number of block, either 1 or 2 or 3 or 4, 5, whatever number of block.
You're not hinting at the capacity.
The index of the block, not the number of blocks. Okay, the index of the block, which is which of those blocks exist in the cache before I start. Remember, the capacity is 2 blocks. So the cache can only accommodate 2 blocks at a time. So which of these 2 already exist in the cache before I start? Remember, I told you the cache is empty. Okay? So the answer of the first row is nothing there. Don't write anything. You can write just dashes. Okay? Now, if you get a hit for the block that you are requesting, you can have 1 over there. If you got a miss, you can add 1. If you follow the second path, you can add 1 over there. And you can see the penalty for each of these operations. If there's a hit, you will pay that cost, 10. If there's a miss, you'll pay 30. If there's no cache, you'll pay 25. Later on, we're going to take the total of all of these ones. You'll have only 1, right? You record as a 1 request, either hit, miss, no cache. Hopefully, you're all done with the first row. Okay. Now, the second row, we already execute something in the first row. So we are supposed to bring that block already in the cache. So now when we start over here, now we are requesting again block 1. What is the status of the cache now? Remember, we already request something in the first row. So there's something to be in the cache. We have to write the index of that block. What already exists now in the cache? Assuming we already done the first row. Don't say. Don't say. Okay? Yeah, just write the index, either 1, 2, or 3, or 4, 5. Now, okay, we already supplied the request in the first one, and we pay some cost. Now, in the second row, we already know what exists in the cache. Now, based on that, whatever you fill over here, and we are requesting block 1 now, is it a hit or a miss or no cache? You need to place 1 or dash or any sign that's indicating that you know that now we are in this stage, or we are paying that cost. Okay, is it clear? If you have any question, please ask right away, because all depends on each other.
But there is no differentiation at this point between cache to non-cache path.
You are not allowed, you see the one highlighted in yellow, you are not allowed to use the second path. Remember that. No, you have to choose that, because you're not allowed to use this at all. You're not allowed to use it at all. No second path. Means if I see any answer in this column, I'm going to do what? No chocolate for 1 week. Okay? All right. Now we are in iteration 1, in the second one, which is we are requesting block 2 now, right? We are still in this square, but we are requesting now block 2. Now we already have something in the cache from these 2 lines, right? From these 2 rows. Each one of them adding 1 block. Could be maybe up to 1 block, because they might be adding the same block. We don't know that yet. Okay. But remember this, the status of the cache before supplying the request. So this is what we have now as a cache before we supply the demand for that block. Okay. Now continue in the same pattern until you complete the entire table. When the cache gets full, means has already 2 blocks, you need to apply the least recently used policy to replace one of the 2 blocks out, bring in the new one that you are asking for. Least recently used means I go in this sequence, I look in the history, which one was earlier in the top of the queue. That should be replaced by the recent one coming in. This is individual effort. This is individual effort. Okay. Whoever finished the entire question, we get a chocolate.
I think
Not you, someone else.
and also, right, when the cache is filled, the question here is, we are not going to empty if there is no new request.
Yes, yes, of course.
That's
of
the
course.
assumption here.
Of course, yeah, makes perfect sense. For example, in the last line, you don't have to do anything with the cache. Please, instead of sitting, ask question. If you don't answer anything, I'm happy to answer. This is not exam. Just ask question that I don't understand. What should I do at this step? I'm stuck. Yes.
When we comes in block 3,
okay.
Like I is equal to 2 in the last third iteration.
Block 3, here or there or there? The middle,
I2.
here?
Yeah.
Okay. It means in I2 last one. Yes.
Yeah. Are we allowed to replace before that block 3 comes?
No, we'll bring it from the memory, but where to place it? It's already waiting here in the channel, memory channel, or the data path. Okay. Remember, what we are going to include over here is before we supply the request. Done? What do you mean, maybe?
I'm not sure what the problem is.
All right. I think Naim, are you done or still checking? Done?
Just cross checking.
Oh, it's still working.
Done.
Done? Your name there? Yes, please write your name, student ID. Who's else done? Okay. Individual work. Individual work.
Yeah.
Can you fill the total miss rate? Total. Yeah, the total, it depends what you insert here. If you insert 1 or tech or star or any sign, meaning I'm choosing this column over this column, then the total number of these signs, right? If you choose to have the penalty over here, like 10, 10, 10, for example, what is the total of all these penalties. So sorry. So it means this and this might have the same meaning, depends on how you write it. Okay, the total latency and total penalty. So it depends on how you show it in the answer. Done? All right. So we have the first two, Nancy, Naim, Jahin. Two of these three will get the chocolate. Depends who answered correct. If you have any question, if you are stuck, just let me know. This is a real straightforward example. Will give you a better imagination of how the cache will get the data. You missed the chocolate?
Suppose one block is already present and one is not.
Where? Here?
The
You can point.
second one
The middle. Yeah.
in the middle here.
One
of them will not be present.
Of course, because the capacity is 2.
So one hit and one miss.
I cannot tell the answer now. Individual work. Individual work. All right, we'll be done soon. Remember, we have another microphone, so your question will appear in YouTube if you want to so. It's over here. If you want to ask a question, you can use it. All right. All right, please keep the paper with you. We are going to answer the second question in the back. Okay, please take your paper. I think Jahim, Naim have correct answer. We have Nancy. Can try a bit more. Abu. Abu. You are Nail. Neil. I think it's perfect. All right, please keep the paper. You deserve half of it. You can share. All right, let's see the answer. So the first one, what should be? It's empty, right? So we have dashes and it's a mess, of course. The cache has nothing in it. Now the second one, we are requesting block 1 from the first try, right? So we are supposed to fill it. Maybe I could have another column over here and showing the status of the cache. So now we already add 1, but this is not from this line. This is from the previous line. So we already have a 1 over there. And now anytime we ask for block 1, it already exists in the cache, so it's always hit, right? So we pay less cost now. Now in the second try over here in I1, we are still over here in this box. We are requesting block 2. We never request block 2 before. So it cannot be a hit, right? It cannot be the last column because we said we are not allowed to use the second path. So now we will have block 2 in here, But remember, this is the status of the cache before supplying the request. So we cannot add 2 over here. We will add it later on over here, okay? But we are working on it in this line. Now we got a miss because there is no block 2 over here. We'll bring it from DRAM, and we have to pay the total cost of 30. So we have 1 over there. It means we are using the 30 over there. As I said, it's up to you. You can write 30 over here. You can add whatever sign indicating that I'm in that column. Now in I equal 2, I start with the next box over there. I request block 1 first, right? Now remember, there's block 1 and 2 from the previous line, not from this line. So this 1 and 2 from the previous work we did over there. Now we are asking for block 1, which is already in the cache, so hit. Block 2 already exists, so hit. The I equal 2 in the third one, we are requesting block 3. We never requested before. So it cannot be a hit again. It should be a miss, right? And then we are missing block 3, but the cache is full now. The capacity is 2 blocks. So we have to do something. We have to take one of them out. Which one? Should we take block 1 or block 2? Least recently used. Which one was just now used? Block 2, right? What was earlier than that? Block 1. What was earlier than that? Block 2, block 1, block 1, and so on. Now, least recently used, among the ones in the cache, which one was earlier used? Block 1. Okay, because block 2, I just use it just right now, and block 1 was earlier. So I should replace which one? Block 1, right? Now I'm here. Yeah, so now I replaced in the next line, not in the current line. Why? Because again, this is the status of the cache before applying that instruction. So now I replace 1 with 3, and this is the current status. Okay, and of course it is a mess since I bring it from the DRAM. Now in I3, I'm requesting block 2, but it already exists in the cache. So it's a hit. And next one, block 3, it already exists. So a hit in I equal 4, block 3 already exists in the cache. So again, a hit. Okay. Now what is the total number of hits? 6. Total number of misses? 3. Right. Now what is the miss rate? Excellent. So a number of misses, right, over, we don't have total memory request, but we have the hit and misses. You have a third case, so it's either hit or a miss. So total of them will give me the total number of memory requests. So that's the miss rate, which is 3/9. Total latency, so how many times we hit, then the total cost 6 times 10, plus 3 times 30, plus 0. We never use that path, so 0 times whatever equal 150 cycles. So now the total cost of your program is 150 cycles. Now, what does that mean? What is cycle over here? You remember we said the frequency, each CPU has a frequency, right? And 1 over the frequency is time. 1 over frequency is the time period, or 1 cycle of the clock frequency that the CPU uses. Okay, so you can go to the Apple logo on your laptop. You can go to the properties or info, and you can see what is the clock frequency of your computer. Normally around 4 gig, 3.2 gigahertz, right, or around that. So 1 over that number will give you the time of 1 clock cycle, normally in nanosecond or so. And you multiply that number by 150, that will give you the total execution time for your program. Maybe 1 second, 2 seconds, 3 seconds, and so on. Okay. Now that is the trivial thing. We use LRU. We didn't use any sophisticated method. We didn't use the other path and so on. Now let's see. Now we change only a little bit. We are allowed to use the second path only for uncached load instruction for block 1. So only whenever we want to fetch a block 1, we will use the second path. Okay. block 2, block 3, we have to go through the first path. Understood? Clear? Any question? Only we want to fetch block 1, we go through the second path. When we fetch the other blocks, we go through the first path. Please use the back of the paper or maybe the same paper. It's up to you. You can write in different color on the same table. Whatever you see more clear. Individual effort. Uncached means there is no cache, okay, for block 1 only. So whenever the CPU asks for block 1, we have to detour over this path. If block 2, block 3, we have to use the first path. Okay. This is a bit tricky because there's no cache over there. So any block going through this path, we don't have to add it to the cache. Remember that. Individual effort. Done. I think it's correct. Remember, when the cache is full, you have to use least recently used. Since the cache fits only 2 blocks, then we just replace the block that we didn't use it in the previous instruction, basically. Yeah.
You never need also whenever like
I think so.
whenever you
No, you never can have in one row you cannot have in any row, one and one and one, or two ones. In any row, it should be single one in the last three columns. You should choose single choice out of these three columns. Either it's a hit or a miss or no cache. It cannot be both of them. Okay, in any row, you cannot choose two columns out of the last three columns. You cannot choose more than one, basically. It's either a hit in the cache or a miss or no cache. Yes. Done. You can try a bit more. This is the second question, right? Yeah, you can try a bit more. Good. Any question? Oh, I see. Yeah, don't cache.
You can't put block one in cache.
Of course.
You always have to put
There's no cache in the second path, you see? Yeah, I think can be correct. Can be correct. No, there's no miss, no hit, because there's no cache. The idea of miss and hit is only for cache. If in cache, hit. If not in cache, miss. Done. If I'm not using cache, I cannot choose hit or miss. All right, as easy as that. Hit and miss only for caches. If I'm not using cache at all, there's no hit and miss. It's always in DRAM. Now, if I'm using storage, yes, there's a hit and miss for the DRAM, because the data might not necessarily be in the DRAM. I have to go to the storage SSD, bring some data to the DRAM, then to the level of hierarchy. Yeah, I think it's correct.
More than finding this rate,
Mhm.
so it will be miss upon miss plus that no catch also.
Excellent. This is a very good question. For the miss rate, how we are going to calculate it? Now we have two paths. What should we do about it? It's easy to calculate for the first path, but over here, now you can make your own assumption. You have one of two choices. Either you assume this way, as we do normally, which is this guy, or you can assume something else. You can assume like anything out of CPU as a request, it's a request. We don't have to care about hit and miss. Anything we send, give me this block, whatever it is, wherever it is, DRAM, cache, storage, whatever, still a request. So it's up to you. Okay? Now keep the paper with you. I think we got enough number of papers. So I think we can consider time's up. So Nancy, great job. Naeem, great job. Jahin, great job. And this is Mansour, I think. Yeah, great job, everyone. I really like that everyone's participating. So let's see it together. We're requesting block one. Block one should be only through the second path, so it's always non-cacheable. We never use cache, so we always through this. Cache still empty. Second request, still block one. We cannot use cache, so don't check for hit and miss. Directly go through non-cacheable. The second one is block two. Now we cannot use the second path. Block two only for first path. Is the cache empty? Yes. Then okay, we still have it empty. Now, since empty cannot be a hit again, because we don't have that block, right? So it's directly a miss. and cannot be non-cacheable because we are not allowed to use the second path. We are only allowed to go through these. Now, in the third request, or fourth, we are requesting block 1. Block 1 through the second path again. So don't check the cache at all. Just skip and go direct to the DRAM, fetch the block from there to the CPU, done. And it will cost you 25 cycle or $25. Now to the next request, we are requesting block 2. We just requested earlier, so it should be in the cache. So we check in the cache. Is 2 there? Yes. Then it's a hit. Now we request block 3. We never requested before, and it's not through the non-cacheable path. So we check over there in the cache. We never requested, so we are not assumed to have it in the cache. So it's a mess. We go to the DRAM, to the cache, to the CPU. And that is with this line. Now in here, we already request 2 and 3, so it's supposed to be in the cache. So anything we request out of 2 and 3 should always be hit. Hit, 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 done. We have 4 hits, 2 misses, and 3 non-cacheable paths. Okay? This is the actual design. This is true architecture. And we are going to see a real example from a number of CPUs that allows to bypass the cache. Okay? Some of the CPUs allow you, through special instruction, to program it yourself and skip the caches. Go from DRAM to the CPU. This is true, especially in GPUs. In GPUs, some of them allows you to go through that to skip the latency, the expensive latency that you might have.
So the reason why for the first line, that was for the reason, because we don't have it first.
Oh, you assume the cache is not empty?
Right.
You use it from the previous question?
Yeah, exactly.
Okay, yeah, this makes sense. This makes sense. If you say so, yeah, it could be correct. Because we never assume cache is empty, to be honest. Because you always load the operating system once you turn on the machine. And that will take space in the DRAM, right? Because to load the operating system along with all the programs, all the application to the DRAM, to the caches, to the CPU to execute them. So whenever we launch our own application, we assume we have some space in the DRAM, but not totally empty. Okay. The same piece of data might be shared among different applications, so it might be loaded in advance. That's true assumption. So now, since we allow for non-cacheable path, what happened with the total latency? Increase or decrease? There is this YouTube video when students don't know if it is increase or decrease, what they say. Jesus, right? Yeah, so this is increasing, right? So why? This is expected because we are not using cache. And the main purpose of the cache is to reduce the latency, to store the data in intermediate.
Doesn't that happen in cache?
No, the question didn't say that. You could assume that, but it's not given. All right. This one, we don't have to solve it altogether, but this is a bit more complex. Now, 2 blocks has to go through the non-cacheable path. Number 2 and 3, okay? In the previous question, block 1 has to go through this. Now, 2 and 3 has to go through this, and block 1 through the first path, okay? Now, maybe we can do it together. Ready? Ready? Okay, let's do it together. Remember, 2 and 3 through this, 1 over that. Now, which one we are requesting first? Block 1. Okay, always through this. Cache is empty. This is our assumption. So directly a miss. Okay, a miss, and cache is empty. Iteration 1, block 1 again. We just requested, so it's already in the cache. So it's a hit, and now the cache has a 1. Now, block 2 should be through the non-cacheable, so here. And remember, don't add it to the cache. Cache only has block 1. Now, directly, you can say that the entire cache would remain with block 1 because none of the other blocks are allowed to be cacheable. Okay? Now, any request other than one, you just go with the non-cacheable. That means there is no cache at all. And then you will see the total cost or the latency really increasing. Okay, and this is again, we predicted, right, to increase the cost if we don't use caches. So in summary, without L1 cache at all for all blocks 1, 2, 3, that we didn't solve it before, but you can expect it as 9 times because we have 9 memory requests multiplied by 25, which is the cost of the second path. So it will give you about 225 cycles. Now I could ask you the question, the exact same question in a different way, how we can reduce that total number of costs or total number of cycles, right? By adding a cache. Okay, you add a cache. That cache, what capacity? Maybe 2, maybe 3. I have 3 blocks in total my program is accessing. What should be the capacity of the cache? If we have it with 3 blocks, perfectly fine. That's ideal, right? There is no need to replace any block. And we place it once in the cache and done. We access it all the time. So if we want to make the program the fastest ever, just increase the number of the capacity of the cache to 3, from 2 to 3 blocks. Then we don't need to replace anything. But if I give you some restriction on the price that you have to pay for the cache, I give you, like, for example, $2 or $4. You're not allowed to use a cache that costs you more than $4. Okay? In this way, you are restricted with certain design. And then you can use like 1 cache block capacity or 2 cache block capacity. And then the question is, which replacement policy should I use? Since I'm not fitting the entire data that my application needs in there. So we already saw something in between the optimal one, where we use the cache all the time, and between not using cache at all. So we can mix between using it and not using it and see somewhere in between. Okay. All right. Now let's continue the same table. Please, now you are not allowed to use the second path at all, but use Belady optimal algorithm. Not least recently used replacement policy. What does it mean? It means you need to look for the furthest block that you are going to use in the future, not in the history. You don't look backward. You don't check which block was least recently used. No, you check in the future which one is really far from my request. I'm going to request it really later on. And that one should be a target to be replaced. Okay. Again, you can assume the cache is empty. Okay. Sorry. Show me. Cache is empty. You start with the first request. I'm going to request block 1. Cache is empty. So it's not a hit, not a miss, no cache. It's a miss, right? Because it's not there. Now I'm going to request block 1 again. Block 1 again. It already exists in the cache because I just requested. No replacement happening. So it should be hit or miss. Hit, right? Now in the second one, I'm requesting block 2. Block 2, I never requested. And I'm not allowed to use second path at all. So always through the first path. So it's a miss. So I have to fetch it from DRAM to L1 cache. L1 cache still available. Now I have 1 and 2 in the cache. Now I request block 1 again. So it's a hit. Block 2 again. It's a hit, right? Now block 3. I never requested before, so it's a miss. But the cache is full. Has 1 and 2 already. What should I do? I have 1 and 2. Which one of them should I replace to add 3? Now I don't look back upward in the history. I look forward in the future. In the future, I'm here. Remember, I'm in block 3. In the future, I have 2, 3, 3, and so on. What is the furthest block that I'm going to request? not the furthest block that I'm not going to request. Okay, this is important. Okay, I don't have it in the cache. 1, it's not in the future. It is? No, it's not in the future. 1 or 2 or 3. 9 said 3, right? 3 is not in the cache. Cannot be 3 for sure. What we have in the cache we need to replace is 1 and 2. How we can replace 3? It's not in the cache. We don't have it in the cache. We need something to replace. We cannot stall the CPU forever just waiting for something to be replaced. 3 is not in the cache. We need to choose 1 or 2. Who's saying 1? You're not saying. Who's saying 2? No one? Who's saying 2? Who's saying 2? Right, let's see. Yeah, whoever says 1, it's correct. Why 1? Why not 2? 2 is really in the near future, just right after this request, next request, right? But 1 really after it. So which one, 1 or 2? 2 is here and 1 is there. So 1 is furthest, right? So we replace 1 with 2, with 3, sorry, because 3 is the new request over there. So we add 3. And now every time we request 2 or 3, it's already in the cache. So it's ahead and done. Okay? Any question? Anything not clear in the previous 3 questions? This is really important to move forward. We're not done with exam questions. The entire lecture is about that. This is to give you a hint about the importance of cache design. Okay, it's not a simple topic. It's really important. All the designers around the world, all the computer architects really care about the design of the cache. There are a lot of choices. What should we choose? Should we go with 3 levels of caches, 2, 1? What's the capacity? What is the associativity degree? What is the replacement policy? And so on. Any question? Yes, John.
Just to replacing 1, be the first step. 1 and first. Well,
Oh, yeah, okay.
is there anything or
This is fully associated, right? So you can replace anywhere you want. It's up to you. But that's really nice note. He said you're always, when you are replacing the first number, not the second number, and then you're replacing the new number in there. So we are replacing 1, so we are supposed to add the 3 at the first number. So here it should be 3 and 2, not 2 and 3, right? Because we are replacing the first number with the new number, which is 3. We are removing 1, put 3 in place. Why now we switch the order of 2 and 3? That's a very nice observation. Yeah, should be 3 and 2, right? To be correct, to be accurate. But remember, this is fully associative, means there is no fixed place for any block. If I said direct map, everything is changing because I need to look at the address. I fetch the LSB bits of the address, and based on that, I can decide whether it should be as a block 1 in the cache or block 2 or block 3 and so on. So you can see, you can play even yourself with this question, tweak it a little bit, and it will be totally new question. Okay? You want to make it more complex? You go with the n-way associativity. You divide the cache into number of sets. Each set has different ways, and good luck. Okay? We saw example of n-way associativity. If you missed that, please go back to the previous lecture, right? Okay, now you can do many more. You can choose the second path, for example, for block 2 and 3. Okay, now block 1 only through this path, block 2 and 3 over here, but you are using Belady optimal algorithm, not LRU. This is the answer if you're interested in it. All right, now enough with the LRU. Last time when you check your cache, most of it was using a variant of LRU policy, right? Most of your caches, right? How many of you check the specification of your computer? 1, 2, 3, 4, 5. I give you that website. If you are lazy to go through the Apple logo and go about, and then you'll see all the specification of your machine, you can go to the link that we provide in the lecture. You can go, for example, to i7, to i9, to i5, whatever your CPU, and you'll see all the specs of your cache. And we saw that most of the policies were a variant of LRU, right? Least recently used. However, now we will jump into a paper, research paper, that's not being implemented in any of the caches, right? So it's still a research paper. And the first author, he's now a professor in Georgia Tech. Okay, he was in Texas, A&M, was doing PhD, and now he's in Georgia Tech. So he proposed this paper in 2006, and it gained a lot of attention, about 400 citation or so. Okay. Now the paper called MLP, we just give you a small hint about it. This stands for Memory-Level Parallelism. Means I'm aware about the hierarchy of the CPU, and based on the hierarchy, I'm going to decide which block to be replaced. Okay, which block in the cache to be replaced based on the hierarchy that you have in your system. So what it says, memory-level parallelism, or MLP, varies. Some misses more costly. This is what we discuss over here. The misses are two types: one parallel, one isolated. Which one is more expensive? Isolated. Excellent. The parallel, we are hiding the cost of some of these requests. Here, like we have 2 requests in parallel, we don't multiply the number of requests times the penalty. So total latency doesn't change because those in parallel. But over here, they are sequential. So if we have 3 misses times the penalty of each, that's the total latency, right? So some misses are more costly than others. And by introducing awareness about the hierarchy, the replacement can improve performance by reducing costly misses. So here we are focusing on isolated misses. Okay, we want to give priority always to isolated misses to be always in the cache. Okay, that is the entire idea behind the paper. Always, whenever we see isolated miss, keep it in the cache. We don't want to replace it. So they have some formula for the cost that they are calculating, right? And they said we can implement that as part of what is called in the cache as a miss status holding register. This is already existing in the cache, okay? A register that storing the number of misses that we are facing, right? And they want to modify the hardware design of the cache itself. Okay, so that is one of the drawback of this work, that they require more hardware to be added to the existing design of cache. They add a field mean more bits. Okay, they add more bits to that register, and they call that field as MLP, makes sense, cost. Okay, what is the cost now of memory-level parallelism? And every cycle for each demand entry in the register, they calculate that, or they update that cost. Okay, 1 over n added to the total cost. What is n? We will see now. Okay, it's the number of demand in misses, but we will see it in practical in one of the exam. This example or question copied from the paper itself. Okay, so you'll see it in the paper presentation back in 2006. We have now two types of requests. The green ones are the cheap one, the parallel ones. Okay, the pink one is the expensive ones. Okay, the green ones, that's why they are all in one box, because they are cheap and they are parallel. And the pink one are costly and they are isolated. Okay, so any miss to any of those blocks in the green are served in parallel, so we don't pay penalty times the number of requests. And any misses to these blocks, we pay to them sequentially, okay, since they are isolated. Now we will focus on two replacement policy. No more LRU. Done with it. Okay, we already got too many examples. Now we'll focus on Belady and MLP. The MLP is Georgia Tech paper. Okay. The goal of Belady was to minimize miscount. Okay, we focus on misses. We don't want to get less miss rate. The goal of the other one is to reduce the isolated miss, because they claim that the isolated one are more costly than the parallel one. So we want to reduce those in particular, not all misses, but we want to reduce these in particular. Okay. And we assume fully associative cache. What does it mean? The cache is all ours. Okay. It's up to us where to place a block in a cache. It's up to us. There is no limitation on the LSP of the address. There are no sets, as in any way associative cache, right? Fully associative. Everything, it's yours. You can place your block wherever you want in the cache. What is the size of the cache? 4 blocks. So if we want to add 5 blocks, we cannot do that. We have to replace one of those blocks and then add the 5th one. Okay. All right. So now let's start with Belady optimal algorithm. This is the initial status of the cache. So we already fill it with something. Okay. What do we have in there? So this is the order of the instructions. Circular, right? We are iterating over all these requests. So we start always from here. So the first request to supply is P4, and then P3, P2, P1. Remember, all of those done in parallel, okay, for the green box. So what we have in the cache is the same order as we have in there. So we already have P1, P2, P3, P4, okay? You can consider this as the first placed one, P4, right? And then the next, the next, the next, okay? Now we want to move from this box to this box. What is the first block that we are asking for? P1, right? Does it exist in the cache? Yes. Move. P2, P3, P4. You can think about it as 4 parallel requests to those P, since all of them are serviced in parallel. So now we move, and the status of the cache is still the same. All those 4 blocks are there. There is no messes at all. Okay. Now here's the trick. Once we move to the isolated block, what will happen? Now remember, the capacity of the cache is 4, so we cannot add the 5th one. So now we ask for I1, which is isolated block number 1. And submiss, we don't have it, and now we need to add it to the cache. Where to add? Which block out of the 4 we need to place I1? Now remember, we are using Belady optimal, means furthest in the future. So look in the future in this circular, which one out of these 4 we're going to use furthest? So let's see. We are here. Look in the future. I2, we don't have it, so don't care. I3, we don't have it, don't care. Move. P4, yes, we have it. Okay, that's a candidate to be removed. Do we have something furthest? Yes. P3, okay, this is a better candidate. Now we move next. P2, okay, cancel P3, P4. We want to replace now P2. That's the best candidate because it's furthest. Now let's move next. Oh, there's P1. Okay, P1 is now better candidate. Cancel the rest. Now B1 is a better candidate. Move furthest, for example, B1, B2, B3, B4, and then I1 and so on. Which one should be replaced? Why? Furthest and the next requests. Any other opinion? Yes.
How far are we?
Excellent question. How far we should look into the future? How far we should look into the future? Remember, to know which block is going to be requested in the future means I understood the next instructions. And in the CPU, I cannot know that. In the CPU, I only have a program counter that's pointing to one instruction. And every time I execute that instruction, I move to the next, the next, the next, right? But I can do some kind of pipelining to parallelize fetching those instruction, right? And then this way, I can know or maybe understand what is the next instruction is asking for, what kind of data I'm requesting, right? It's always risky to keep going with the next instructions. If you allow your CPU to fetch like 10 instructions, it will be more expensive than we allow it to parallelize or pipeline with only 2 instructions next, and then 3 instructions, 4 instructions, right? So that is a very good question, how far we should go. Now, ideally, we should look within the near future. If we keep going, we need to allow the CPU to fetch all those instructions and read them and execute them and understand what kind of variable we are requesting and where they exist in the memory, whether they are miss or hit. Okay? You got it. So that can be given in the question, for example. You can look into next 10 instructions, for example. Within the next 10 instructions, you can decide which one is the furthest. Or if it is not given, you can assume that. I'm going to assume next 4 instructions or 4 different blocks, for example. Not based on the instruction, but different blocks. Okay? Painful for the architect who designing that CPU. Larger block in terms of cache block or in terms of window time frame where I'm looking into the instruction. Yeah, however, if I'm extending this time frame, I'm paying more cost to the CPU. The CPU has to fetch more instruction and understand, not only fetching, understand each instruction, which kind of data is requesting. This is how I'm going to decide what's the next request. Is it B1, B2, B3, right? By bringing more instruction, and each instruction I'm going to decode it to know which variable I'm requesting, where are these variables, are they in different blocks or the same block, okay? So P1 is correct. P1 is correct. Sounds logically and cheap in a way that I would choose the near future that's close to me, okay? But again, we could tweak the question to ask for more. Right, so now we have a miss with I1. We replace the P1 with I1, okay? Why we replace P1? Hopefully it's clear to you because we look in the future and we saw that P1 is near, P3 just near, close by, P1 is the furthest, okay? Now we have I2. I2 is a miss because we don't have it in the cache. So we need one of them to be replaced because the capacity is only 4. Which one to be replaced? P2. How many say P2? 1, 2. Again, you can Ryan also, okay? P2. Let's see. Let's go in the future. We are now here in I2, not in here. We have I3, not here, so we don't care. We go there. P4. Yeah, want to change your answer? I1. Okay. So now we can agree on something. We can agree on something. You can see, for example, this might be the easiest way to look at it. You can check what is inside the cache, okay, and decide which one of those will be at the first time, appearing the first time, be furthest, okay? Which one inside the cache will be requested again furthest? This might be straightforward and easy way to apply, okay? Which one already in the cache will be requested, re-requested again furthest, okay? So let's see, P4, just right here, just first time. P3, first time is just here. Okay, now P3 exceeding P4, so P4 no more candidate. P2, what is next? First time over here. So P2 now exceed all of them, so it's a candidate. I1, it's already furthest, right? So requesting again I1 is really the furthest compared to P4, P3, P2. So I1 is a candidate to be replaced. Now, how far we should look? The same question. Is it costly? How to implement it? What is how expensive this algorithm to be implemented? No wonder why it's not implemented now in any of the CPUs, right? But might be implemented in microprocessors or something special, like special purpose rather than general purpose. Then we are replacing the I1 with I2. And now we have a hit. Now I3, same question. Which one to be replaced? Because I3 does not exist in the cache. Let's follow the same idea. We look at P4, the first time it appears over here, P3, P2, and then I2. Which one furthest? I2, right? Hopefully this way there is no confusion about it. Now there's a mess. We remove I2, we add I3. Okay. Now we iterate, and we do this and this until we got this for the entire cycle. What happened over here? Every time we got a mess, we got what we call a stall, meaning the CPU stopped doing its job. It's frozen, right? Go to the memory, bring the data, come back, continue. So we stall how many times? 4, because we have 4 misses, right? And that is just like cartoon implementation of the total number of cycles that we consume. But you can follow our previous question, do that table, and based on that table, you can get the accurate number of cycles. But let's assume is this many of cycles, okay? Or total latency, if you say so, because stall is different number of cycles than hit. Now, we apply Belady optimal algorithm. Want to apply the next one, which is MLP-Aware. Okay, MLP-Aware. Yes.
So just to the reason why this delay before it because you then
So for isolated, yes, because it doesn't care or it's not aware about the memory hierarchy. It doesn't know the cost of each request. So it does not differentiate between isolated one and non-isolated one. So it's not like it's targeting the isolated to be removed all the time. It has nothing to do with isolated. It doesn't know that this is isolated miss. It just happened because those are coming after those requests. If it is the opposite, like those first before those, then they will stay. Okay? Because they will not be furthest. These three requests, if they are here and this green box over there, it will be totally opposite story. So the isolated one will stay in the cache. The green boxes will get replaced. It doesn't know which one is isolated, which one is not isolated. Mhm.
So could it be like the processes that are already immediately?
Then now you are moving to the software level optimization, right? Because how we place those requests before those, that's the program. Whoever wrote that program, he requested those data before those data, right? But you could have like hardware aware implementation of the software as we did last time. You remember with the matrix multiplication, what kind of compiler optimization we did over there, because we know that the C language is the row major, so we did something. Likewise with switching the for loop, because we know the hardware, how it was implemented or oriented, then we could do that optimization. Now let's see the second algorithm. In total, we have 4 misses and 4 stalls. Makes sense, okay? But now let's apply the MLP. Now this is the initial status. In the previous question, all of them, we assume empty cache, but here we assume a certain status to the cache, okay? The current status of the cache has P4, I1, I2, I3. Why? It just consider this area of execution. P4, I1, I2, I3. It's assume it start executing from here. Okay, that's the assumption they made. Now we have hit for I1, I2, I3. Now we move to the next one over there. Okay. Now the first one we got over here from this request is P4, right? Is it in the cache? Yes. So hit P3, not in the cache. So we want to replace something in the cache with P3. Now we are using MLP, and we said MLP is based on, raise your voice. Yeah, memory-level parallelism. But which block should be replaced? The least costly one, right? The least costly one, which is P4, because P4 is parallel or serviced in a parallel, so it's the least costly out of everything in the cache. Whenever we have the isolated one, we keep them. Okay, so we replace P4 with P3. Now P2, it's a miss. You have to replace whatever cheaper. And when we got P1 is also a miss, we want to replace the P4 or P2 with the P1. So by the end of that block, we will get a P1, I1, I2, I3. Okay, got it? Okay, now next. What is the right next block? P1. We don't have, we have it already, so it's a hit, right? What is the next after that? P2. Does it exist? No, so we have to replace something, which is P1. We don't have it, okay. But we replace P1 with P2, then P3, then P4 with P1, and that will get 3 misses out of that. But P1 is already a hit because we already have it before executing that. Probably we are missing one animation after this to show what is the content, but probably because it went back to the previous status of the cache. So if you remember what we have in the cache earlier, we have P4, I1, I2, I3. That is the initial status of the cache, right? And after executing the entire block over there, we will return back to the initial status, which is P4, I1, I2, I3. Yes, please. No, servicing them in parallel. But the order of requesting them, it's still maintained. Meaning, only the difference is the cost I'm paying to supply those services, the request. So when I access over here, I access in sequential order, all of them. So I access P1, give me P1, P2, P3, P4, right? That's in sequential order. But now having all these blocks is done in parallel, okay? You don't have to pay 4 times for the miss rate, for example. Now let's see it here. Maybe it will be clear. Let's see how this execution time or the stall will be different, okay? Just because of those parallel requests. Let's see. What happened here? We got 3 misses, but the stall is 1. It's actual 3 stalls, but the number of those affecting the latency is not sequentially. So when we see, 3 stalls, but the penalty we pay for them, it's the same as 1. Okay? That's why the execution time is shrinking. Likewise, with over here, we have 3 misses, but the number of stalls are 3, but we treat them as 1 because we don't pay triple penalties. Okay? Although the misses are still 6. The misses are still 6, not impacted. But what is impacted? The latency or the stall. The amount of time the CPU is hold or frozen for execution. Okay, that's the stall. Now, looking at the 2 algorithms, what was the goal of the first one? To reduce the misses, to optimal in number of misses. This is what we are saying, right? If we look at the misses, this is 4 and 6. Is it successfully reducing the number of misses? Yes. 4 is less than 6. So this is optimal in terms of reducing number of misses. Now, if we look at the second, what was the goal of MLP-Aware? Reducing the cost of isolated misses, right? Because they are the most expensive one. Now, if we look at the execution time, is it successfully reduced compared to this? This ending over here, but this execution time is ending over there. And we have less number of cycles to execute the program. That's why we have less number of stalls. So which one is better? Which one is better? Excellent. Deserve chocolate. Although the number of cycles is less, but we cannot tell that this is really less than that. This is better than that. Why?
And this is a very important message because this is telling us that the replacement policy that provides the fewest number of misses is not necessarily providing the best performance. And performance here, again, it could be in different metrics. For example, performance, we could measure it as number of cycles, for example, to execute instructions or to complete program execution. But that's a very important aspect, that those algorithms try to focus on one aspect, on one side of the problem, and then try to optimize it in terms of that aspect. For example, we saw that the Belady optimal algorithm, it's really optimal in terms of number of misses. However, in the MLP, which is Memory-Level Parallelism Awareness algorithm, try to be optimal in terms of the number of cycles or reducing the number of cycles when we have isolated misses. So in general, we don't know in advance whether those isolated misses are there or not. And we cannot claim that MLP-aware algorithm is always optimal, for example, because if we don't have that much of isolated misses, then we cannot reduce really the number of cycles.
If you have the chance to choose one of them, which one you will choose? Now let's forget about the number of misses. If I ask you about the number of cycles, the second one, right? Even though it's still a research paper from Georgia Tech, and probably why it's not implemented, it's because the hardware cost, or how you're going to implement something aware about the cost of the request without knowing if it exists in the level 1 or level 2 or level 3. So they took a little bit about the implementation and that they need cost calculation logic to be added to the register to know that the cost of every request we are requesting the memory to give us that memory block, right? However, this logic calculation is really expensive. Give me just 5 minutes. I'm going to show you example of this hierarchy, and then we will be done with the caches totally, right? And then we can move to the DRAM in the next lecture. So please, you can have a look at the caches. When you go home, you can open these links. You can see the architecture of the CPU and get more glimpse about the cache size of each of those processors. Here, this is Pentium 4. How many of you remember Pentium 4? This is a very old computer, right? You can see the cache is half of the CPU because the CPU was not capable, was very slow, right? So it was not doing a lot of computation. That's why it's really small. And the L2 cache is half of the processor. You can imagine. Turbo? Yeah. To increase the frequency of the CPU. Yeah, probably Pentium 2 is for floppy disk. There's no operating system. There is only DOS. And you insert a floppy disk for a game or something, and then you execute some command to turn on the game. Yeah, here is Apple M1. Now we have M4, right, for Apple Silicon. So you can see the caches over there. They have a different naming in Apple than Intel. Over here, you can see how those caches are becoming many, but also small in size, or in ratio compared to the entire CPU architecture. But they are becoming really many. So we start, instead of having only half of the CPU to the cache, now we start having smaller ones, but really many of them. Why is that? Because the CPU start having more cores, and each core will have its own private cache, and then we will have some of them shared among all these cores. Now here, same story, but this is AMD. This is Ryzen. Ryzen is for AI, so this is AI accelerator. This is again about 3D stack level. We will talk about this in the next lecture, or maybe the next week when we start introducing the processing near memory. This is IBM Power 9, and this is a bit old. And this is streaming multiprocessor. You can see most of it here is caches. This is NVIDIA, a GPU, and something interesting about Hopper. This is Hopper architecture, which is the things we discuss. We will see it in the next lecture, but now we discussed already that some of the GPU allow you to go from the DRAM and bypass the L2 directly to the scratch pad or the register in the CPU. Here, this is a GPU, right? So we have a GPU core doing the calculation as in CPU. So we can bypass the L2 directly to the cores. And this is in A100 GPU. In V100, we cannot do that, okay? Now in H100, we can also do that, and we can do more. This is the H100, which is Hopper architecture from NVIDIA. Here we have the global memory. We have L2 cache, but also we have here multiple of these. What are these? What is SM? streaming multiprocessor, which is, you can think about as a core or a CPU. This is a GPU, right? It has a lot of threads in each of these streaming multiprocessor. So we have cores, we have the register, we have also shared memory and L1 cache. Now, you can see the number of cycles to get a data from the global memory. So it's really expensive. So if you want to accelerate something in GPU, try to minimize the number of times you go to the global memory, okay? Every time you go to global memory, you pay the most cost, okay? So those architecture allow you to bypass L2, so you kind of skip half of the price because you don't need to store it in L2 and then again to the L1 cache. So you directly bring it in there. You still pay some cost, but still way cheaper than accessing the caches. That already exists in the A100. What is special here? So this is direct copy. They already have instruction for that, so you can use it in CUDA programming. What they allow also to have the shared memory between multiple streaming multiprocessor to be also directly accessed. So if a data exists here and that streaming multiprocessor asks for the same data, they don't have to go to the memory and request it. They can share it among that as if those caches are also shared among the streaming multiprocessor. So you can go from streaming multiprocessor to streaming multiprocessor and copy data back and forth. That's what's really special here. So the GPU has these high-speed communication medium between the global memory and there. So that's why you can get very fast data in a cheaper way of doing it. That's the summary of the entire lecture about caches. So please go over it. So it's talking about special thing for level 1, level 2, level 3. Please go over the example, the exam question. You can come up with your own question. You can really be creative in building this question and do a lot of assumption. You might improve some of the research paper and so on. So if you're interested in this, you'll see a lot of papers about caches. Okay, so hopefully, I think there are 2 or 3 papers about caches. We will see a lot of interesting talks. I'm really happy from the paper that you choose, all of you, especially around LLM and security. I see a lot of papers around these 2 topics. So hopefully it will be fun. And remember, if you have any requests, please ask as soon as possible to change the date or swap talks. We will try to consider that now. After that, it will be very difficult. And for those who are presenting in the first week or 2 weeks, they need to contact us as soon as possible. We need to decide on the date on when they are going to practice their talk, okay? It's already a month and a half from now, so you have a bit of time to review your paper, prepare your slides, and so on. And please hand over the paper that you write your name on it and you solve the question. That will be considered as attendance. Yes, please. Hand over all papers. Make sure you have it, even if you have only your name written and that's it. Make sure to submit it, because that will be your attendance.
Do we have here the J puzzle?
Jay.